We're going to skip around a little bit. We're going to move on to section 4.3, and then we'll go back and take a look at other aspects of the unit circle. But it might be nice to sort of ground some of this work we're doing in terms of right triangle trig, which is something you're probably at least a little bit familiar with from high school geometry. You may not have seen radians before, but you've certainly seen sine, cosine, and tangent in the context of right triangle trig. So this seems like a good time to take a look at that and try to make a little bit of sense out of this. And then we will go back to sort of connect this to the new stuff we've been working on. So sine, cosine, and tangent. Maybe people don't remember every definition, but you remember something about SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, and it spells SOHCAHTOA. Look at this right triangle we have over here. So I'm going to make angle C my right angle, and I've got an angle theta down the bottom over here, right? That's the Greek letter theta. That represents an angle measure. So if I want the sine of theta is a relationship between two sides of my right triangle. So it's the relationship of the opposite side to the hypotenuse. So if I start with this theta, B is the opposite side, and C is the hypotenuse. The hypotenuse is always the side that's opposite the right angle. So in this right triangle, you notice that the capital letters name the angle, the lowercase letters opposite that angle name the side length. All right, so cosine is adjacent over hypotenuse. So what's adjacent mean? It means right next to it. Technically, it's adjacent leg over hypotenuse because there are two things that are both adjacent to this angle over here, right? One of them is this side here, side C. The other is side A. But out of those two, which is the adjacent leg? It's A, right? The hypotenuse is not a leg because, well, it's a hypotenuse. All right, so the adjacent leg is A. The hypotenuse is C. And then tangent is opposite over adjacent. So tangent is the one of those three trig ratios that does not involve the hypotenuse at all. It's the opposite leg, which is B, over the adjacent leg, which is A. All right, so sine is opposite over hypotenuse, cosine's adjacent over hypotenuse, tangent is opposite over adjacent. All right, well, that's good. Can we apply this to something? This triangle here I know is a right triangle. And even if I didn't mark angle C as a right angle, I noticed that I can use the Pythagorean theorem and say 8 squared plus 15 squared is 17 squared, right? 64 plus 225 is 289. So the sine of angle A, right? So we always have to look to see what angle we're taking the sine, cosine, and tangent of. The sine of angle A means we start up here and we look for opposite over hypotenuse. So the opposite side is 15, the hypotenuse is 17. What if I want the cosine of angle A? Well, the cosine of angle A is adjacent over hypotenuse. So the adjacent side is 8. The hypotenuse is 17. And then tangent, again, we start up here at angle A. Tangent is opposite over adjacent. So the opposite side is 15. The adjacent side is 8. Now, if I go and I look for sine, cosine, and tangent of other angles, then that changes my perspective. So if I want sine, cosine, and tangent for B, the cosine of angle B is adjacent over hypotenuse. So from angle B, the adjacent side is 15, the hypotenuse is 17. The sine of angle B is opposite over hypotenuse. So go to the opposite side, right? The opposite side is 8. Hypotenuse is 17. And tangent is opposite over adjacent. So we said the opposite was 8. The adjacent was 15. Now, the sine, cosine, and tangent of C are going to present a little bit of problem to our definition because opposite angle C is the hypotenuse. So it turns out if I find the sine of 90 degrees, the sine of 90 degrees is 1. You could think of it as the opposite side is the hypotenuse, so they're both the same. The cosine of angle C, well, the cosine of 90 degrees is actually 0. And so there's no nice trig definition like what's the adjacent side to C. There's two adjacent sides. And eventually we're going to find out why this is the case. And then tangent, it turns out, when we say opposite over adjacent, well, the opposite leg is the hypotenuse. And so we're just going to say that it's undefined. Now you notice the way that I set this up. The sine of angle A and the cosine of angle B, they turn out to be the same number, right? They're both 15 over 17. The cosine of A and the sine of B are the same thing. and the tangents of the two are just reciprocals, right? We flip them over. It has to do with the fact that A and B are complementary angles. Complementary angles are two angles whose measures add up to 90 degrees. And so here I have two angles whose measure adds up to 90 degrees. A and B are complementary. So the sine of an angle and the cosine of its complement are the same. The cosine of an angle and the sine of its complement are the same. And for tangents, the tangent of an angle is the reciprocal of its complement's tangent. So what do I do now knowing these sines and cosines and tangents? Well, it turns out that I can use them to actually find angle measures. And you're going to do more of this as the course progresses in future sections. But just to give you a little idea as to where this is going eventually, suppose I want to find the measure of angle A. The measure of angle A is dependent on either the sine or the cosine. I don't know, let's pick the sine. So if I know that the sine of angle A is equal to 15 over 17, then the measure of angle A is the inverse sine of 15 over 17. Now, on your calculator, you're going to have to check a couple of things. First thing is, you're going to have to check to see what mode you're in. So on my calculator, on the bottom corner, it says DEG for degree. If you're not in degree mode, if it says RAD for radian or GRAD for gradians, then you're going to have to hit the DRG button or go to your menu and flip back and forth. So make sure it's in degree mode. Then you've got to find the inverse sine. So on my calculator, I have a sine button, but then I also have on top of the sine button a sign with a little -1. That's the inverse sine. So on my calculator, I got to hit the second button and sine, and it opens up a set of parentheses because that is what produces the inverse sine. And then I type in 15 over 17. All right, so did I just take a picture of my calculator? Yes, I did. So first of all, you notice down in the corner I've got the DEG. This is telling me I'm in degree mode. If it says RAD, then what I have to do is I got to hit the DRG button and put myself in degrees back into radians. The other thing is, if I want the inverse sine, then I got to hit this second button over here and the sine button, and that'll give me the inverse sine. So on my calculator, everything that's in blue above the buttons is accessed with that second. So you notice I hit second and then sine, so that's what gave me the sine with a little -1. That's inverse sine. Then I typed in 15 over 17, and I got 61.927. So if I want to round to the nearest tenth, then it's 61.9, and my answer is in degrees, because I'm actually finding how many degrees the measure of that angle is. So which measure was it? It was A. So the measure of angle A is 61.9 degrees. Now, if I had done cosine, try it. Do the inverse cosine of 8 over 17, and you should get the same thing. Once I know the measure of angle A is 61.9, I know the one at angle C is 90, so if a whole triangle adds up to 180, measure of angle C is 90, so the other two have to add up to the other 90. So the measure of angle B is 90 minus 61.9, 28.1. Right? So that's 28.1 degrees down there, and you could have done that by finding the inverse cosine of 15 over 17. It'll give you the same thing. So every once in a while, I'll ask you for the measure of the angle, and you do the inverse trig function. Eventually, we'll get to a whole unit on inverse trig functions a little bit down the road. All right, so this just tells me I can set it up. So let's look at a couple of applications here. Beam is supporting a roof slanted at an angle of 38 degrees from the horizontal. The horizontal distance on the beam is 4.6 meters. How long is the beam? So the beam is coming down like this, right? That's the wooden beam that's holding up the roof. It says 38 degrees with the horizontal. So the horizontal goes left to right, so that's 38 degrees with the horizontal. How long is the beam? Well, what am I looking for? That's the beam over there. This down here is the horizontal distance under the beam, which is 4.6. Now, what do we have? We have an angle, right? The angle is 38 degrees. We have the adjacent side, which is the 4.6, and we have the hypotenuse. So now I got to go back and ask myself, what trig function relates adjacent over hypotenuse? Well, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So the cosine of 38 degrees equals the adjacent leg over the hypotenuse. All right. So we've got two numbers and a variable. How do I get rid of that denominator? So multiply both sides by b. B for beam. So b times the cosine of 38 degrees equals 4.6. And now divide both sides by the cosine of 38. Remember that the cosine of 38 is just a number. I don't know what it is. My calculator can tell me that. But whatever the cosine of 38 degrees is, that's going to be the number that I'm dividing by. So now I grab my calculator and I type in 4.6. Try this and make sure your calculator is in the right mode. 4.6 divided by cosine of 38 gives me 5.837. So if I round it to the nearest tenth, 5.8, right? I was given dimensions to the nearest tenth, so I should probably round to the nearest tenth. 5.8 what? 5.8 meters. And it should make sense that the beam is longer than the horizontal distance, because if the horizontal distance is 4.6, if I laid the beam down, it would be longer than 4.6. So how long is it? 5.8. So I set up my cosine ratio. Cosine is adjacent over hypotenuse, and then worked from there. All right, this one we're going to need to do up on the top. It says 20-foot ladder is leaning up against the wall, makes a 25-degree angle with the wall. How far from the wall is the base of the ladder? All right, so a 20-foot ladder. So again, the 20 feet is the hypotenuse. Here's the wall. Here's the base. Here's the ladder. So this ladder over here, there's the rungs on my ladder. 20-foot ladder. Leaning against the wall makes a 25-degree angle with the wall. 25-degree angle with the wall is this angle up here, right? This is the wall. So a 25-degree angle with the wall is right up there. Not the angle down the bottom, right? That angle down the bottom is a 25-degree angle with the horizontal. 25-degree angle with the wall is up at the top. How far from the wall is the base of the angle? So that's the distance I'm looking for. So based on that angle up at the top, I've got the opposite side, right? The opposite side is the x, so that's what I'm looking for. The hypotenuse is 20. Opposite over hypotenuse is sine. So set up the ratio. The sine of 25 degrees equals opposite over hypotenuse. And this one is easy, because if I multiply both sides by 20, I get 20 times the sine of 25 degrees equals x. And then I grab my calculator, I type in 20 times the sine of 25, all in one shot, and I get 8.45. 8.45 what? Well, if it's a 20-foot ladder, then I must be measuring in feet. 8.45 feet. So this distance here, it's just under 8.5 feet from the wall. All right, another application of these right triangles are angles of elevation and angles of depression. Angles of elevation and depression are always measured from the horizontal, and basically you're looking up for an angle of elevation, you're looking down for an angle of depression. So you're on a plane. Plane descends at an angle of depression of 15 degrees. If it travels 16,000 feet on its descent, how far above the ground was the plane when it started its descent? So here's the plane. Right? Looks more like a Goodyear blimp, but it's a plane. And so the plane is descending at an angle of depression of 15 degrees. Now, the pilot's looking out at the horizontal. Angle of depression of 15 degrees means 15 degrees from the horizontal. It travels 16,000 feet. How far above the ground was the plane when it started its descent? So I'm making myself a right triangle. Now, I'm going to dig back into your memories of high school geometry here. That 15-degree angle up at the top is outside the triangle. But we got two options. One option is if these two lines are parallel, this angle over here and this angle over there are actually the same. Remember we call those a pair of alternate interior angles? The other option is to say, well, it makes a 90-degree angle here, so if that's 15, this angle up at the top here must be 75. All right, so let me redraw the picture here. That's a 15-degree angle over here. That's 16,000 feet. What I'm trying to find is how far above the ground the plane was. So based on that 15-degree angle, I've got opposite and hypotenuse. That's sine. Sine of 15 degrees equals opposite over hypotenuse. Now, if you had gone to the other angle, if you had said, well, why can't I use that 75? Sure you can. Except instead of being the sine of 15, you'd be using the cosine of 75 because you'd have adjacent and hypotenuse. Adjacent and hypotenuse is cosine. I hit both sides with a 16,000. 16,000 times the sine of 15 degrees equals h. And so now if I multiply 16,000 times the sine of 15, 4,141 feet. All right, so that's how far up in the air the plane was from the ground straight up to where the plane is. A little over 4,000 feet. So angle of depression 15 degrees, which is kind of a nice ride, right? You don't want that angle of depression to be too big. Otherwise, you're going to be taking a nosedive down to the runway, and it's going to be a turbulent landing. So we don't want that to happen. All right, reciprocal trig functions. Reciprocal trig functions are used in calculus. There are a lot of formulas that still use reciprocal trig functions. Reciprocal means flip it over, right? So the reciprocal of cosine is called secant. And we'll get into this a little bit further. The reciprocal of sine is called cosecant, and the reciprocal of tangent is called cotan. So if you've got a right triangle with sides of 9, 12, and 15, we've got to first draw the triangle, then we've got to pick an angle. So let's put 9, 12. Two shorter ones are always the legs. That's the hypotenuse. So let's call this angle theta. So the sine of theta is opposite over hypotenuse. So opposite is 9, hypotenuse is 15. 9 over 15 simplifies to 3/5. Cosine of theta. Cosine of theta is adjacent over hypotenuse. So adjacent is 12, hypotenuse is 15. 12 over 15 simplifies to 4/5. Tangent of theta. Tan of theta is opposite over adjacent. So opposite over adjacent simplifies to 3/4. Now, what if I want the other three? What if I want secant of theta? The secant of theta is the reciprocal of cosine. So if cosine is 4/5, secant is 5/4. If I want cosecant, cosecant is the reciprocal of sine. So if sine is 3/5, cosecant is 5/3. And then cotan is the reciprocal of tan. So if tan is 3/4, cotan is 4/3. Now you'll notice all of the trig functions we've done for sine and cosine, we've never gotten anything bigger than 1. And that has to do with the fact that the hypotenuse is always the longest side of a right triangle. And so if you're comparing either the adjacent side or the opposite side to the hypotenuse, you'll never get anything bigger than 1. On the other hand, look at those values for secant and cosecant. Both of those are greater than 1. So if you take a number that's less than 1 and you flip it, you're going to end up with something that's greater than 1. All right, at some point maybe you've learned about special right triangles. So 45, 45, 90 triangles and 30, 60, 90 triangles. All right, so I got some writing space over here. Suppose I start with a 45, 45, 90 triangle. Sometimes this is also called an isosceles right triangle, because suppose I called these two sides 1, right? The opposite sides, if they're opposite congruent angles, they're congruent to each other. Use the Pythagorean theorem, you find the third side is the square root of 2. So the sine of 45 degrees is opposite over hypotenuse. But oftentimes we're going to simplify that. We're going to rationalize the denominator. So multiply top and bottom by the square root of 2. The sine of 45 degrees is the square root of 2 over 2. The cosine of 45 degrees, oddly enough, is the same thing, right? Because instead of looking at the opposite side, we'll look at the adjacent side. But it's the same thing. It's still 1 over the square root of 2. Square root of 2 over 2. What's the tan of 45 degrees? Tan is opposite over adjacent. 1 over 1 is just 1. These are very important. Sine of 45 degrees, cosine of 45 degrees, square root of 2 over 2. If you were doing these in terms of radians, they would be pi over 4s. Tan of 45 degrees is 1. All right. What about a 30, 60, 90? Well, you can actually take an equilateral triangle and split it in half. And that's where the basics of a 30, 60, 90 come from. That's 60, half of 60 is 30. So in a 30, 60, 90, it turns out if that's 1, hypotenuse is double the short side. Side opposite the 60 is square root of 3 times the short side. So in a 30, 60, 90, it's organized like so. And then any multiple, right? 2, 4, 2 square root of 3 also makes a 30, 60, 90 triangle. So now we've got multiple sets of values. The sine of 60 is opposite over hypotenuse, so opposite over hypotenuse, square root of 3 over 2. The cosine of 60 is adjacent over hypotenuse, so adjacent over hypotenuse. And then the tan of 60 is opposite over adjacent, so square root of 3 over 1 is just square root of 3. Now, suppose I go up to that angle up at the top, right? That 30-degree angle. So suppose I look for the sine of 30 degrees. Sine of 30 is opposite over hypotenuse. Oh, it's the same thing as the cosine of 60. And now if I asked you for the cosine of 30 degrees, cosine is adjacent over hypotenuse. It's the same as the sine of 60. The tan of 30 is opposite over adjacent, so it's 1 over the square root of 3. But then if I rationalize my denominator, I get square root of 3 over 3. All right, we'll do more with the reciprocal functions later, but like if you want the secant of 45 degrees, the cosecant is going to be the same thing. They're both going to be square root of 2. Cotan of 45 is still going to be 1. For the 60s and the 30s, the secant of 60 is the reciprocal of the cosine, so that's 2. Cosecant of 60 is the reciprocal of the sine, so it's 2 over the square root of 3, and so forth. All right, so these complements are things we kind of already talked about, but let's go through them kind of quickly again and take a look. The sine of an angle and the cosine of its complement are the same thing. So over here, the sine of theta equals a over c, right? Opposite over hypotenuse. The cosine of its complement is up here, right? 90 minus the angle, is adjacent over hypotenuse. Same thing. It turns out the same thing's true for tangent and cotangent and secant and cosecant. They're complementary functions. So the tan of the angle is opposite over adjacent, so a over b. The cotan of 90 minus theta, so cotan flip over the tangent. So instead of doing opposite over adjacent, we do adjacent over opposite to get cotan. So adjacent is a, opposite is b. Same thing's going to happen for secant and cosecant. So this is all done in degrees. If you want it done in radians, there it is in radians. So they call them the cofunction identities, right? Because sine and cosine, tangent and cotangent, secant and cosecant. The sine and the cosine are also complementary functions. The other thing, too, is that if you have something in radians, then the 90 gets replaced with a pi over 2. All right, so I know this is getting a little bit long. We got one more thing to take a look at, and then we'll wrap it up. So this says find a cofunction with the same value as the given expression. So the cosine of 22, we know cosine and sine are related to each other. So the cosine of 22 must be the sine of 90 minus 22. What is that, 68? So the cosine of 22 is the same as the sine of 68. If you don't believe it, throw them both in your calculator and see that you get the same thing. All right, the tan of pi over 6 must be the same thing as the cotan of, instead of 90, we'll use pi over 2 since we're in radians here. Pi over 2 minus pi over 6. Ooh, fractions. Pi over 2 is the same thing as 3 pi over 6, right? That's half a pi. 3 pi over 6 minus pi over 6 is 2 pi over 6. And 2 pi over 6 simplifies to pi over 3. So it's true that the tan of pi over 6 is the same thing as the cotan of pi over 3, right? Those are complementary functions. We also call them cofunctions. Good. So we took a little walk through right triangle trig there today.